So resistors. We know the resistance of a resistor depends upon how it's made and what it is made of. So rho is the resistivity of the material, L is the length of the material, A is the cross-sectional area of how it was made. A resistor has a potential difference across it if there is current flowing through it. We know if we have a complete path connecting one end of a battery to the other, then current can flow. So we're going to draw a resistor as little squiggly line as if it were the filament in a light bulb. We are assuming ideal wires. So connecting wires, we are assuming the resistance of them is 0. With that assumption, the delta V is 0 for connecting wires. So in this circuit that I have drawn with this one resistor, the current will flow. It will flow specifically clockwise with the way I've drawn the picture. So it comes out of the positive terminal of the battery and continues all the way through until it points into the negative terminal of the battery. Now, when we were talking about capacitors before, we talked about following a path. And as we followed a path from one end of the battery to the other, in that situation, capacitor, but the same rule is going to hold here in that any element we pass by is going to have the same voltage as the battery. If there's multiple elements we pass by, then their voltages are going to add up to equal the battery voltage. If we have one single resistor connected to our battery, that resistor will have the battery voltage, the EMF, across it. That means we could calculate this current knowing that battery voltage and the value of our resistor. That's this equation. Ohm's law. The voltage drop across this resistor is the EMF of the battery. Thus, if we solve for current, we get the EMF of the battery divided by resistance. It is possible to connect resistors in series and parallel. That general definition that we talked about before with capacitors is the same, meaning if you follow a path from one end of the battery to the other, and you have to pass by the multiple resistors, then they are in series. So we did not have a choice of a different path to take. And that's what means they are in series. If I draw current flow, it flows all the way around. It comes out of the positive terminal and continues through each and every resistor until it enters back in at the negative terminal. Current is the same for all resistors in series. That was similar to capacitors having the same charge. Here we talk about the flow of charge though, so current. Now each of these resistors will have a potential difference because they each have current flowing through them. If I follow my path, from one end of the battery to the next, going around this loop, I find that this battery voltage has to be shared amongst these three resistors. I called them V1, V2, and V3. By the way, that's called a loop rule. We'll talk about that more as we continue. But that battery voltage has to be shared amongst those three resistors. They're not necessarily going to share equally. In fact, if they're not the same resistance, they will not have the same voltage. Right? Delta V is equal to IR. So delta V1 would be I times R1. Delta V2 would be I times R2. Delta V3 would be I times R3. What would we put in for the battery, though? Well, if you recall what we did with capacitors, we said we could talk about an equivalent value. So similarly, we can talk about an equivalent resistance, meaning one resistor whose values or number of ohms would behave the same way and cause the same amount of current to flow if the equivalent, I'll put equivalent down here. So R equivalent is the value of one resistor that would result in the same current flow as having these three resistors in our series circuit. So in place of the EMF of the battery, I can put I times R equivalent. But I is the same. In series, there's no junction, there's no different paths for the current to take. And so they have the same current. We find with resistors that calculating the equivalent resistance for resistors in series means we simply add the resistors together, the resistance values. Now, this is backwards from the capacitors. When we had capacitors in series, we had that 1/over relationship. This is just opposite. And gratefully, we don't have to remember which is which. We have the test notes with the appropriate equations in it. So just jump there and make sure you're using the right equation for the right circumstance. Parallel, similarly, is when we have a battery, but then there's junctions that allow current to flow in different directions or down different paths. So if I start drawing this current that comes out of the battery, I'm going to use it I sub t for a total current. That's ultimately what will come back into the battery as well. But because there is a junction here, some of it will go this way, but some of it continues up. So it continues up and reaches another junction. So ultimately, this total current ends up splitting off three different ways. Some goes to the top resistor, some goes to the middle resistor, some goes to the bottom resistor. Let me make this a little bigger so I can label. This is an R1, an R2, and R3. Similar to the series circuit, we can treat this as having an equivalent resistance, meaning what one resistor could we put in here that would behave the same way? And by that, I mean draw the same amount of current as the total current here with these three resistors. So in terms of conservation of charge, we can write our equation that represents the junction rule, the total current that flows out of the battery and eventually back in this case, gets split amongst those three resistors. From our Ohm's law equation, we can say I is the potential difference over the resistor. But if you recall with capacitors, they all had to have the same potential difference. That's going to be true here as well. And that's because if we follow any one path from one end of the battery back to it, we only pass one resistor. And if the battery voltage has to end up being across the element we pass by, then they each end up having the battery voltage across them. So when I write this out, my I total I'm going to write as the battery voltage over the one equivalent resistor we could essentially use to represent this circuit with three. I1 using this equation is going to be a delta V1 over R1. I2, same equation, but for resistor 2. I3, delta V3 over R3. But the voltages are the same. So when resistors are connected in parallel, we have an inverse relationship to find the overall equivalent resistance. So we can look at problems with multiple resistors similar to what we looked at with capacitors, where we may need to combine our resistors in parallel series, however they're combined down into an equivalent resistance, and potentially work backwards to find the current. One of the biggest things to keep in mind, thinking about this equivalent one resistor connected to a battery, the current that flows depends on the battery voltage and the equivalent resistance. Meaning, if they're in series, even if they were the same three resistors, connecting them in series versus parallel, I don't know what that's trying to do. Okay. All right. Connecting three resistors, even the same three resistors in series versus parallel, leads to a different equivalent resistance, and thus would lead to a different amount of current flowing through the circuit. In series, since we simply add the values of resistors together, we get a bigger number. So coming back up to our equation for current, a larger R equivalent value means a smaller amount of current. In parallel, when we use this inverse relationship, R equivalent is always smaller than the individual resistors. Meaning, if R equivalent is a really small number, then the current is really big. But if we think about it in terms of them all needing the same potential difference, then hopefully that makes sense. The current has to pump out, or the battery rather, supposing it can, has to pump out enough current to flow to each of these individual resistors to give them the same potential difference. So whenever we connect resistors in parallel, we draw more and more current from the battery. This is the idea of not plugging too many things into a power strip. the wiring in our home is in parallel in terms of any given outlet. So if you put a power strip in, you're now allowing multiple things, so multiple resistors to be applied or powered, and you draw more and more current, which the wires are not ideal. The connecting wires do have some resistance, not much, but some, and that means the current is going to cause the wires to heat up. The thermal energy is going to increase, the temperature is going to increase, and we run the risk of starting a fire, essentially. So we are going to look at some examples of having resistors in series versus parallel, but then we are also going to look at some problems where we specifically have to use the loop rule and the junction rule. So we'll talk about that more as well. We've been talking about it as approaching these problems, but we will see some circuits where we cannot find an equivalent resistance, so we have to write equations based off of the loop rule and junction rule.